Hey Shane, how are you?
I'm good. How are you?
Good. Um, I can't remember where we left off. I think it was like 46.
Okay.
Is this not the right button? Oh. So we did this one.
Okay.
I know.
Okay. Um, so yeah, which of these, well, I guess you flagged the ones.
I mean, I would still go over things because I feel like even if
Mm-hmm.
like I wouldn't just do incorrect.
Mm-hmm.
'Cause yesterday showed that sometimes I guess correctly, and even if I forget to flag it, it's still something I want to know completely.
Yep. So how did you do this problem?
What was the equation that it was? I can't. Like F, um, forces like and something over times distance. Work equals FD. That was it. And then I think that's how I did this one.
Yep.
Force times distance. And then so we have the force. It's 300.
Mm-hmm.
The distance is 0.1.
Mm-hmm.
And that's it. The 0.2 doesn't get used.
Well, so that'll give you the work or the energy, right?
Mhm.
But what are they asking us for?
Third, what is the maximum height?
Yeah, of the of that arrow.
Uh-huh.
So tell me how you're gonna find that.
Isn't it just a straight equation where like V final, like if you're just taking into consideration, it's the opposite of like when it's falling down, it's being shot upwards.
So,
It's
but
like VF VI, like one of those equations.
well, the only information we have about the arrow,
Is the mass.
yeah. So you're going to be using. Oh yeah, I think I have the same thing. I was gonna turn mine. Yeah. Um. So okay, you're thinking about kinematics formulas, which will help you figure out stuff like, well, like if you have velocity, you can figure out like whatever acceleration, time, distance sometimes. But here,
Mhm.
where what we want to do is we want to use.
The work
Yep.
we calculated
Yeah.
is 30,
Uh-huh.
and then the mass. But if you multiply these, you'll get a smaller number. Oh, but there's also this.
Can you hear me?
Yeah.
Okay. There's like really
Use this
loud.
the gravitational field too.
So yeah, so you have the energy of the um like stored in the bow, and
Hmm.
then when the archer like shoots it straight up in the air, you can use that energy that you've calculated, um, and then through conservation of energy, because if something goes up, what type of energy does it gain?
Kinetic.
Well, it'll gain that, but I
On
mean,
the
if
way
something,
down, like at the like
oh,
highest point, it's potential, right?
yep. So gravitational potential energy, right?
Mm-hmm.
Do you remember the formula for that?
Uh-uh.
So it's mgh.
Okay. So that's mass times gravity, 10 times 0.2 gives
Mhm.
us 2.
Okay.
And then our height, we don't have the height.
Yeah, that's what we have to solve for.
Oh, so is the potential 30?
Mm-hmm.
So then it's 30 divided by 2,
Yep.
which gives the 15.
Mm-hmm.
Okay.
Yeah. So a lot of times you can solve problems that normally you would think to use kinematics for, but you can solve using conservation of energy.
But how does the work become gravitational potential energy? Is it like the potential to do work? Like what are we?
Yeah, yeah. In physics, the definition of energy is the ability to do work.
Okay.
So you can use them interchangeably for the most part.
All right, got it.
Yep.
I remember being really confused about this one because like the way that it looks based off of the question, I would expect it to be the opposite curve. But I chose this answer because none of the other ones had the like
Okay.
inverse path.
Well, if it's thrown vertically upwards,
So then shouldn't Oh, well, this is what you were saying about kinetic energy decreasing, and then once it reaches the highest point, it's like potential energy, and then kinetic energy increases again as it falls, right?
exactly, yeah. When
Right.
the person throws it, you already start off with kinetic energy, and
Right.
as
Okay.
it travels, it gets, yeah,
Okay.
slowed down because of gravity. And
Makes
so at its highest point, it's going to have a kinetic energy of 0. And then it'll start to fall, and look at it come back up again. Yeah.
sounds good.
Mhm.
This is the equation, right?
Um,
MGH is
oh yeah,
gravitational
potential.
energy.
Yep, yep.
But then
So now, yeah. So now power
Mhm.
is just the rate at which energy is being used or, given off. So it'll just be energy over time.
P equals E over T.
Yeah. So, um, and the unit would be watts,
Yes.
and like 1 watt is equal to 1 joule per second.
Uh-huh. I guess knowing that the equation has to come in, then it would have been between C and D.
Yep.
And then with this equation, the power equation, it's D, right?
Uh-huh.
I was kind of confused because this is like, I mean, shape-wise, they're all kind of weird, but I figured that these are like as close to the middle of the shape itself as possible. And then this one is like on the top portion, so it doesn't work. I don't know if
Yep.
I was thinking about it the right way. I was just trying, like, from a geometry standpoint, that these look like kind of central.
Yeah, yeah. So they're all, located at the center, it seems, but D is the only one that has underneath it
Hmm.
like nothing. So it's gonna cause it to tip
Okay.
over.
Good. I'm surprised I got this one. Oh, I didn't.
Okay.
I thought it would rotate. Well, I knew it would go in opposite directions, because,
Mm-hmm.
but I feel
So like, let's imagine this
like
is
it
a door.
depends where you apply force, no? Like where's if
So
it's
so
rotated about its center, I assumed it would be closer to the center than on the ends.
so let's pretend this is a door, right? Like over here, and let's say so the doorknob is usually like around here, but imagine it being around here, and you're opening the door.
You
That's
would
not,
look at them like this way.
yeah, like imagine, so I have like a notebook, or what, it's gonna get blurred out, but like, would it be best for me to open it like close to the spiral? I know you can't see anything, but okay, something like this. So, like, would it be better to open it like from here?
No.
Here, right? Would it be
Yeah.
better?
Um,
So, if you think about torque, which is essentially like the force that you applied across like the distance, you get a
mhm.
larger torque. You get a larger torque with a longer distance.
Okay.
Also imagine like a lever. Like imagine like you had something and I'm using my pen as like a lever to lift it up. So if I have a longer lever, right? I don't
Uh-huh.
have anything that long around me, but I would increase the torque and you would be able to lift it up even more so.
Okay.
So torque, you could think of both like the equation that has, it's essentially like the work equation, but it's like going to be 90 degrees. Um, and that shows that torque would increase with distance, but also from a intuitive standpoint, which is how you're looking at it, like so it is true that this would still, rotate about its center, but they're asking for what would rotate with the highest torque, and it would be this. Almost like also if you, I don't know if you ever took like a quarter or something and you like put it down on like a table and you flicked its end and it starts to spin. Have you ever done that?
Mm-mm.
Yeah. So yeah. If you imagine this is a coin, like, yep.
And how it would like spin.
Uh-huh.
Okay.
So wait, does this make sense?
No, it does. I feel like the door analogy worked better for me
All right, so tell me why this is a better choice.
because you would open it from the side. But I like conceptually I understood that it had to go in opposite directions, and you were talking about torque and like what that means for um like this versus this, but I understand that like if you apply like if it's about the center and you apply force here, then it like opens,
Yeah.
both.
So, but that would be the same thing with this, right?
Yeah. No, because the place where you apply the force is what like makes it easier or harder to like open
Okay. So,
because
okay.
it's closer to the center. Like it requires more work
Okay.
to be applied
All right.
as opposed to A.
Okay. And this is exactly what I
We
was
did.
saying earlier.
I remember this problem. I thought we did it together. Um,
Uh,
where you drew something out like this yesterday.
um,
But
yeah.
in order to lift the heavy load with a smaller force, would I
Oh,
thought pivot to the
yeah.
left would put the pivot in the center, And I was thinking like a seesaw situation, like it's usually in the middle, no?
So yeah, for a seesaw, but if you had a seesaw where it's in the middle and you have like a 500 kilogram weight here and like a 100 here, like
500 would be
yeah.
significantly lower.
So let's see if we like where to move that pivot to make it balanced. Which direction would be?
Would you move it more like here? I don't know. Can you see my mouse?
Yep. So if you moved it
'Cause-
there, it would gain even more torque because if you're thinking about torque, like let's say this is a pivot and this is a force that you're applying, this would be the distance r and torque, and this is the force. Torque is that force applied times that distance. I mean, there's a sine theta there too, but that just means that it's perpendicular.
Okay.
So you can see that torque increases as you increase the distance from that
Distance
pivot.
from the larger object. Like that's what you're thinking of, because I was thinking that the force, like, so you would move it more towards the 500?
Yep.
Okay.
Yep. Because the torque between this and the fulcrum, or like the distance there, right? If you move
Uh-huh.
this pivot to the right, as you were saying, that would increase
The
that
torque.
distance. Yeah. And since
And the
it
same with moving the pivot to the left, that also increases the torque. So it should be moving the pivot to the right
so when we're saying torque,
or decreasing the
specify
distance.
we want to specify what torque we're talking about.
The load.
So here in this example, if you move this pivot to the right, the torque will be higher for the 500 weight. Okay.
Okay. All right, so I understand. So here where we want to decrease the distance to the load, which would decrease the torque on the load.
Okay.
So if the pivot can't be moved to the right, then the load has to be moved to the left, right?
Okay.
But wouldn't moving himself closer to the pivot also decrease the distance?
So yeah.
So like, how do I know that B is correct and not A?
So if you move the heavy load to the left, the torque of the heavy load decreases.
Uh-huh.
But if you move the pivot to the
Oh,
left,
because it decreases the distance, but if you move him closer, it doesn't change the pivot or the load distance, so the torque stays the same.
so you want to think about there's two torques happening, right? So there's one torque happening between the person and the pivot,
In between
and
the pivot
there's
and
an
the load.
and then yeah, there's another one there. So if you move the pivot to the left, like let's say here, and it's there, you're increasing the distance between the load and the pivot, which means the torque of the load is increasing,
Mm-hmm.
which is what you don't want. So what you want is the distance between the person and the pivot to either increase, or the distance between the load and the pivot to decrease.
Mm-hmm.
So if you increase the distance between the person and the pivot, the torque of the person would increase. And also, if you decrease the distance between the load and the pivot, the torque of the load would decrease.
Got it.
So, like, think about if you want to use like a lever for something, you want that lever to be as long, like if it's long enough, like there's like, I think Archimedes said, if you have he's like, give me a long enough lever and I'll be able to lift the world. And that's true. So you want, if you want the torque to increase, you're going to have the lever, the distance between the pivot and the person, larger, or the distance between the load and the pivot smaller.
Mhm.
So, yeah.
Okay. That makes sense. Book rests. Isn't it normal force would be the opposite of gravitational force because they're like in this scenario they're opposite of each other. And so
Okay.
you do 200 divided by 10 and you get 2. W equals force times distance. Or that's
Well,
not the right equation, but
the W here isn't work.
right, it's weight.
Yeah.
But I'm just trying to visualize it, and I feel like normal force is always opposite of gravitational, unless
Yep.
it's on an incline. No, but even then, just
Yep.
for
So that
purposes.
that's what we see.
Uh-huh.
So you just have to calculate the normal force.
Right. But am
Yep.
I right? Is it 2? Like, is that how you get to the answer?
What? What did you say?
200 divided by 10.
Uh, so why would you do that?
Because wouldn't that give us normal force?
Well, how would you calculate force? What do you need?
We don't have distance or work.
All right. But how would you normally calculate force?
Work divided by distance.
Well, no, I mean like no, like so like Newton's second law, right?
Mhm.
Like, you know,
Oh, the other P equals E over T? No, that doesn't work either.
it's like it's more it's like the first thing they teach you in physics about forces.
But they're like
Like
inverse.
the formula for a force.
Remember.
So it's F equals ma.
Mass times acceleration.
Yeah.
Wouldn't that give 2000?
Well,
Well, that's acceleration due to gravity.
so think about units.
200 grams and 10 kilograms.
Well, 10 newtons per kilogram.
Right. So we
Okay.
have to convert 200 to kilos,
Yep.
which would be 0.2,
All right.
and then times 10.
Yep. Okay.
Is my
So
solution with this.
you want to make sure that you uh know like the formulas, especially that one, because that's like the most important one in physics. That's like Newton's second law, F equals ma. And you also want, like, I know you like to do like kind of like random things with numbers, and that might lead you to the right answer in this case, where if you do 200 divided by 10, it would, or whatever you said, but it has to be, it has to be like a reason for it.
Mhm.
So, so if they're asking to calculate the force and they give you the mass and the gravitational field strength, you should be able to figure out the force. Also, if you look at the units, right,
Mhm.
you would see that,
I
like, if
think
you
when
did,
I was doing it, yeah, that I literally just converted grams to kilos and left it as 0.2.
uh, I think you did something with like dividing it by 10 or something, but
But that would have given me the 2.
no, but I mean, that's what you're saying now, like that the way to do it would be dividing it by 10. But you
I'm
want to,
trying to like approach it from a new side now, like as I'm going over it with you, not doing what I did before because it didn't give me the right answer.
oh yeah, but I mean, but you're just like kind of randomly doing it, like randomly doing like 200 divided by 10 or something like that. But you want
I
to have like
Yeah, okay.
a reason for
Understand.
doing
I
it.
agree.
So force, like definitely get the like formulas down, like try to do that before our next session. Like there aren't that many, but like literally like Newton's second law is, F equals ma.
Mm.
So they're asking you to just calculate a force here. And
Pretty
so,
sure Blueprint had a
well, in Anki, there's
yeah,
a
I know.
deck fundamental equations. That's probably the
Oh,
fastest way to get
shit.
it all memorized.
Okay.
But
Makes sense. I agree. I've done that one, but
oh,
in the
like
past. Give
Anki,
me 2 seconds.
so Anki, it's not about like doing it before or not. It's about doing a little bit every day so you don't forget.
Repetitively, I know.
So yeah, so you definitely want to know at least F equals ma. That's probably like the most important one. Um, but yeah. What are you trying to show me?
Give me a second. I know that there was like resources and there was a thing that's like PDFs and equation sheet. This.
Yeah, there's tons of equation sheets, but
Okay.
you know, they don't mean anything unless
Go over.
you know them. So yeah.
There was like a block there. Oh, got it. Okay. All right, let's go back to Jack Weston and keep going.
Okay, so do show me the calculation of this using
The
um
equation. F
yep,
equals ma.
yep,
Okay. So mass is 200 grams and acceleration due to gravity is 10 newtons per kilograms. So you have to
okay,
convert 200 grams to kilos, which is 0.2,
okay,
and times 10.
hmm,
The kilograms cancel out and you're left with 2 newtons.
perfect, good.
I remember doing this one and having to convert the meters to like centimeters, but
Hmm.
I didn't know like in which way to combine it in the
Hmm.
end
Hmm.
because I don't know, because this is like you have to convert kilos to grams. I don't know.
Yeah, the cubic meter to cubic centimeter could be pretty tough to calculate. Um, so we can do something like, let's see, um, the
Like a math shortcut.
uh, kinda, yeah. So let me think. Um, I'm pretty sure it'll be like a million. Um,
But do you have to do the cubics if they're both in cubic, like meters and centimeters?
What do you mean?
Doesn't it cancel out and you just take the cube root of like 6,000?
Like, but what do you mean? Like, in what situation are you
Like when
talking
you're
about?
solving for this. Like because it's like m to the third and cm to the third.
So what about that?
Like wouldn't you just like negate the cubes and like
Well, a centimeter is not a meter.
I know. So then you just do the regular like meters to centimeters or centimeters to meters thing.
So tell me what you mean.
No. It's like the craziest way of confusing me. Like as in,
Well, I
okay.
mean, because you're saying if they just randomly cancel out, but they like how would they do that? They would have if things can only cancel out if they have the same units.
Uh-huh.
So
Okay. You're right.
so we can do so like let's decide what unit to convert something into. Like if we want to do it as meters, cubic meters or cubic centimeters.
Wouldn't meters be better?
Okay, let's do that. So I could write, I'm gonna write like what 1 centimeter would be in meters, and it would be 1e negative 2
Mm-hmm.
meters is equal to 1 centimeter, right?
Mm-hmm.
Because so 1e minus 2 means going backwards like this.
Yes, yes, I know.
Okay, so now if we had, let's say, 1 square centimeter, this would be 1e negative 2 meters squared, which would give us, what should that give us?
1 e to the negative 4
Yep.
meters. Got it. Okay. And
Square
so
meters, right?
this one, since it's cubed,
Mm-hmm.
it's 5. Do you
So,
add them or no? You multiply them. 6.
yep, negative 2 meters cubed. Oops. Yep, there you go. So, okay, so air has a density of about 1 kilogram per cubic meter. So, okay, if this, so this means that 1 cubic centimeter is equal to 1 millionth of a cubic meter, right?
Mm-hmm.
So alternatively, that could also mean 1 million cubic
Centimeter.
centimeters is equal to 1 cubic
Meter.
meter. So, you could now just memorize that for the future. But yep, so that's what you would do.
Okay. So that gives us,
Mhm.
and then do we,
Yep. So now if we're given this density here and we have this volume here and we're being asked to find mass, what do we do?
don't you have to
Mm-hmm.
multiply
Mm-hmm.
this number, this 600 centimeters cube number?
Uh-huh. The 60,000 one, yeah.
6,000,
Go on.
sorry.
Keep going. Multiplied
By 1 kilogram over.
Mhm.
So 1 kilogram over m cubed is equal to x over 6,000.
You could do it this way, like with like this multiplied by, so now 6,000 cubic
We
centimeters.
have the 1e to the 6 centimeters cubed that we could use instead of it.
Uh-huh.
But
So
also,
we
never mind. So
yep.
6,000 cm cubed over 1e to the 6th cm cubed gives us 1e to the 3rd cm cubed. Like, does it cancel? Can it?
To use something like that.
Why do you have so many centimeters? Where does where the kilo can?
So 1 kilogram per cubic centimeter, and then I multiplied it by the conversion factor, right?
Uh-huh.
So for in 1 cubic meter, we have 1e6 cubic centimeters,
Uh-huh.
and that'll cancel out the cubic meters.
Uh-huh.
And then we multiply by the 6,000
1
cubics.
kilo by, yeah.
Yep. And then that'll give us our answer in kilograms, and then we'll just have to change that into grams. So this would be like 6e3 over 1e6, which is 6e3 minus 6, -3.
Sorry.
And then that's in kilograms,
And in
right?
grams, you add 3 to that, and or
Uh-huh.
no.
Yep.
Oh, it
So
is.
so in 1 kilogram, there's 1e3 grams. So then it's just, 6e-3, oops, times
Listens.
1e3,
And
which
then you got
is, yep.
that was confusing.
Yeah, I think this is tricky
Do
because it's
they
very,
give questions like that, or is this like exceptionally difficult for?
oh no, they'll give questions like that. But if you have this memorized, it can save you the time of doing this type of uh
So just like memorizing this kind of stuff added to an Anki flashcard. Like
uh
I wrote it down on my notepad, but
yeah, just this part.
yeah. Would that make it easier like for overall conversions?
Mm-hmm. Because then
Okay.
you would know that, and also know that a cubic centimeter is the same thing as a milliliter. Like in doctor TV
Yes,
shows,
yeah.
they say things like we need 50 cc's stat. Cc is just cubic centimeter, which is a milliliter.
And cubic centimeters is a millimeter.
Milliliter.
That's so interesting.
Yep.
I didn't know that.
Yep.
I guess it makes sense. Because
Mm-hmm.
like syringes never have like CCs on them.
Mm-hmm.
Okay. What's next? Is it just half
So
of it because it's half of the sphere? Is the PS to PW normally 1?
um okay, so for this type of problem where we have stuff with buoyant force, we're gonna do, so like for instance, whatever, say this is like floating in some liquid, and you have, the force of gravity bringing it down, mg, its weight, and you
Mm-hmm.
have a buoyant force in the opposite direction, and
Mm-hmm.
that is going to be rho, or the density of the fluid, times the volume of the fluid that is displaced, times g. Okay. Now, the big thing to do here is to understand that, well, if rho is density, that's mass over volume, right?
Yeah.
So if you multiply density by volume, you should be getting a mass, right?
Yes.
Good. So this mg thing here, we can equate to density of the object times the volume, of that object times g. So now this enables us to use this and this together.
Right.
Okay. And now we have to just think about how, if one half of the object, so buoyant force overall means that, if something is submerged or whatever, floating or whatever, it must displace its own weight in the fluid of the water, if it's water. So if half of the object's volume is submerged, that means one half of the object is equal to one half of the fluid, which basically means that these are going to be equal. So if they're asking for the ratio of the sphere to the water, right, we can say that
Would be half of it.
yeah, sorry, I made a mistake here. So the volume of the fluid displaced is equal to one half of the volume of the object.
Mm-hmm.
So then we can do like, so yeah, so then the ratio of the object to the density of the object to the density of the water would be, well, we could equate these two. So rho of the object, one half volume of the object times g is equal to rho of the water, um, volume of the water displaced, and then the g. And now we could just divide, you know, the rho of the water on both sides. And then divide this on both sides as well. Because we're trying to just solve for rho of the object over rho of the water, right? So first I'm going to divide both sides by rho of the water. So I get rho of the object over rho of the water. And then I'm going to just divide this part on both sides.
Mm-hmm.
So that will give me a 2 times, volume of fluid displaced times g over the object g. And then
Mm-hmm.
these will cancel,
Cancel out. And
and
you're
that'll
left
give
with
you a
2.
2. Yep. So these types of problems can get tricky.
Mm-hmm.
So and I know this had a lot of stuff going on, but yeah, they'll definitely ask you something, a question about buoyant
Okay.
force. Like I've
Focus.
seen this on like, mhm. Yeah, usually if it's completely submerged, it's a lot easier because then the volumes will just be equal. But since it's half submerged, it'll have to be like that.
Shane, do you mind if I run to the bathroom for a second?
Yeah, go ahead.
All right, let me just. Okay.
Mm-hmm.
Um, this one I took a guess on. I
Mm-hmm.
remember struggling with it quite a bit.
Okay. Um, all right, so we have this manometer thing here filled with liquid mercury, and it's used to measure the air pressure inside of a balloon, which is attached to one of the ends of the manometer. The other end is open to the atmosphere. The setup is shown below with the height of that and the pressure of that. So, okay. So we can say that this is the atmospheric pressure on that open end of the tube, right?
Yeah.
Okay. And then what's pushing against this part should be the pressure of the balloon, right?
Yes.
Mm-hmm. Okay. Now, let's say that the levels were equal. That would mean that the pressure of the atmospheric pressure would
They
be
were equal.
equal, yep, to the
Pressure of
pressure
the ball.
of the balloon, right?
Yes.
So here, do you think,
But it's not equal, so I'm assuming that the distance, the height
yep, so
is
which one do you think is higher here? Well, when I say higher, I mean,
has more pressure.
mhm.
I think the ball.
So let's say that from here, that we increase the pressure of the balloon
Wouldn't it push it further upwards?
on this side, right?
Mm-hmm.
Yep. Here, though, what do we see?
That even though it's higher up, that means that the pressure of ATM is higher because it
Yep.
pushes it down more and lower and towards the balloon.
Yep. 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 So we know that the atmospheric pressure is larger than the pressure of the balloon, right?
Yes.
And they said the atmospheric pressure is this many pascals, right?
Uh-huh.
And, this would come out to like 100 kilopascals, right?
Uh-huh.
And
That
they're
means it has
asking
to be lower.
exactly. Yep.
And the height is
So,
50.
yeah. So now the last part. So, like, great job at understanding that, intuitively. Um, so now we just have to do like a little calculation to figure out how much lower it's going to be. And that's just going to be like by like rho g h basically. Like
Okay.
the overall equation would be like PATM plus rho GH. That's like,
So,
yeah.
right. And rho here would be this value.
Yep.
So we have 1400
Yep. 14,000.
or sorry, 14,000 kilograms per meter cubed.
Mm-hmm.
We have 50 centimeters, so that's important to change. We said that 1 meter cubed was 1 e⁻⁶ centimeters cubed.
Okay.
So we'll keep that into consideration in a second. And then 10 newtons per kilogram is the gravitational acceleration.
Mm-hmm.
Okay. Now we can knock out the kilos first.
Okay. So now for the meters. So I think before,
0.5 meters 2 meters cubed is e to the third,
So
the negative 3.
So okay. So if we're converting like cubic centimeters to cubic meters, that's where it's that super annoying thing that we did earlier. But thankfully, if it's just cubic meters and like meters
Meters
or
cubed.
something,
Oh, do you just
yeah.
take the cube root of
So like for
the
instance,
1400,
at
14,000?
so for instance, meters over meters cubed would just be like meters goes into meters once, meters goes into this, like,
What?
sorry. So yeah, this means that this would just be 1 over meters squared,
Mm-hmm.
right?
Okay.
Hmm.
1 over meter squared times 14,000 would be 14,000 meters squared, right? Like it's just in a
Uh-huh. Yeah. So Pascal is like newtons per meter squared,
yeah.
force over area. So the meters here cancels and meters goes into this thing, making it go to turn into meters squared.
Mm-hmm.
So that's pretty much it. So then basically I would do like 0.5 is like one half of 14,000 is 7,000.
700, 7,000.
Yeah. And then 7,000 times the 10 is 70,000. And this is going to be in newtons per square meter, right? Which is in
A
pas.
Pascal.
So we have 70,000 uh
Pascals, which would be 7 kilopascals or 7.
so it'll be, we'll take out this 1,000 part, so it'll be 70
Yeah.
kilopascals. Now it's just a matter of, are we, well, it's going to be that we're subtracting it by that amount. So the P atmosphere here, we're going to subtract by this value.
Uh-huh.
So so we have the 100 kilopascals here. So basically it'll
Minus
be,
70. Oh, and we get
yep,
30 even.
yep,
Okay. That makes
yeah.
sense.
So
Is
for this, yeah,
there a shortcut with this? Or this is a problem where like to actually solve it out.
yeah. So like first you would look at it like, you know, intuitively to see that, hey, they're the levels are not equal, and the level, water level, or mercury level for the one that's exposed to the atmosphere is lower. So that means that the pressure of the balloon must be um, lower than that of the atmosphere. So right away we can eliminate like A and B. And then we have to do the math part. And, instead of doing like the entire equation like this, if you just think about it conceptually, we can see that this rho GH term is how it changes, meaning pressure of the balloon would be like pressure of the atmosphere minus this term, whereas on this end, it'll be pressure of that atmosphere plus this term.
And so that would give us like, okay.
Yep. And then just also remember that a Pascal is, a unit of force. Sorry. It's a unit of pressure, so it's force over area.
Mhm.
Mhm.
Okay. Um, Okay, so I
Yep.
thought that it's too small of a distance to be 100 or 150, and then just thinking like logically that a meter of depth would probably wouldn't increase the pressure so much just from like I don't know. It was definitely an educated guess to get to 10% of an increase, but I was thinking of like do you know like divers have I don't know, I've never seen it happen, but I always see like on shows and whatever they have like the tank with the dial that shows like the increase in pressure and you as you go down, and the more you go down the like lower the pressure gets. So I thought that it would make sense for it to be A because
When you say lower the pressure, you're talking about the
the higher the
pressure.
pressure, the like the greater the number.
Uh
The lower the depth, the higher the pressure.
yeah, yeah. So yeah, there is a shortcut for this, and it's basically like for each you gain 1 atm of pressure for each 10 meters you um go down in depth.
What is the conversion of like so from 1 to 2, from 1 to 10, it would be 100?
Um,
Like what is the
so
ATM to percentage? Absolute pressure
oh yeah,
percent.
what percent does the absolute pressure experienced by the diver change? Okay, so I guess we could probably make a proportion here. So if it's 1 atm for every 10, x atm for, well, I guess this is I guess this is like a change, well, of one, right? So because I'm doing like a change, right? Like
Mm-hmm.
going from 1 meter to 2 is a change in 1 meter. So if you do this, we just get, 1 is equal to 10x. Therefore, x is equal to 1 over 10, which is 0.1, which is 10%.
10%.
Mm-hmm.
But that's the change
Yep.
per meter.
Uh, sorry.
That's the change that occurs per meter. So from one
Oh,
to
yeah, yeah. I guess, yeah. If for every 10 meters you have a change in 1 atm, that would mean for every meter you'd have a change of 0.1 atm.
Okay,
Yep.
cool.
So like, I think the Titanic is like 400 meters submerged.
I feel like it's more. 400 meters isn't that much. Isn't it like miles down? It has to be kilometers.
Um, let's see. Oh, 4,000 meters submerged. So that's going to be 400 ATM.
Mm-hmm.
So imagine if you were in that carbon fiber little thing, you know, you're
That's what
every
I was thinking of too when I saw that problem.
yeah, that means that's 400
4
times
kilometers.
that's 400 times the pressure we're experiencing right now.
Mm-hmm.
So like there's nothing left of that. It's crushed to atoms.
Combusts or
No, just straight up from the pressure around it, that's 400 times what we experience, just compressed and
but it's not
crushed.
just like it turns into like a thin little sheet of paper, right? Like it like the on a molecular structure it also happens. So
Yes.
there's not even like wow.
Yeah. Yep. Yep.
Okay. This one, do we have time? Yeah. Okay.
Mhm.
I'm like not used to like the hour and a half, so I was like concerned that we were going over.
Mm-hmm.
Um, I didn't know what turbulent flow was.
Yep.
I was thinking of like the only thing I can think of turbulence is like on a plane.
Yeah. So so this is kind of like well, this is how, you
When I thought of the plane analogy, I always think of like
uh-huh,
I don't know. I've seen the videos of the ta like flight attendants saying that it's basically like the plane is in jelly. Like you won't
uh-huh,
feel like what's going on speed-wise outside,
uh-huh,
inside. So then I assumed that it would mean like no disruptions within,
uh-huh.
and that's how I got B, but
Good, 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 good. Yeah, so generally speaking, like you want your flow to be streamlined, like going in these lines. And like, if this is a wing of a plane, the plane is designed such that, and also like with any type of like field lines or whatever, streamlines and stuff, if they're closer together, it's a stronger
Mhm.
thing than if they're further apart. So like for a plane, the wing will be a certain shape that would make it so that the streamlines
Go
underneath it,
faster over and slower under, right?
oh, just the other way around.
Okay.
So they go faster under. Um,
So that's like how
and
birds glide, right?
mhm.
Okay.
So uh so okay, so when it comes to um wait, did I say?
What's up?
Oh yeah. So sorry. So one sec. So okay, if you have like let's say something like this, just like this random thing that's in the way, and it causes the flow to be no longer in that streamlined flow, but turns into these like swirls
Like it
or like
turns in on
eddies.
itself?
Yeah, like whirlpools or eddies or swirls and stuff. That's turbulent flow. It's no longer going in that straight line. And so when we talked about like taking someone's blood pressure, that's what you do. Like when you compress it, you make it such that you create turbulence and then you can like
Measure.
hear
Mm,
the thing. Yeah.
cool. So streamlines are straight lines. The velocity of a fluid is continu well,
Yeah.
only if it's acted upon, right? Like, why would the velocity change? Then, like, just this the cup of water that's sitting, like,
Mm-hmm.
until I picked it up, it was completely still. Why would the velocity be changing?
Mm-hmm.
So wouldn't this one be wrong too?
The velocity of the
Of a
fluid,
turbulent
uh-huh, at any
is
given point
changing.
is continually
Yes,
changing.
okay, because there's something acting upon it. It is typical
So
fluids.
so these like straight line ones, their velocity is not changing.
Yes, okay.
But yeah, here when they
Understand.
turn into those whirlpools, they do change. Oh, and I was wrong about the wing thing, by the way. So it actually goes, you're right, it goes faster. Oh, sorry. It goes faster above it than below it. And there's an inverse proportion between the velocity of the air and the pressure. So if it's high velocity here, it's low pressure, and underneath it'll be low velocity,
High
high
pressure.
pressure, and that's why it'll cause lift.
Cool.
Yep. All
I
right.
think this is just an equation thing.
Yeah, so this will be, I'll show you a shortcut for this as well. Because a lot of time, like this is makes people think a lot of times about like fluid dynamics, but the fluid, this is like, it's not really like a fluid moving. So we can really treat this as anything that we're just straight up dropping. Like, I think I went over with you, like if I had some ball up here right before I drop it, right, it has, let's say this is like some height. So right before I drop it, right, it's not moving, so its
Yeah,
initial
so
kinetic
VI is
energy is
0.
0. Yep, and its initial gravitational potential is at a max. And then when it hits the ground, like right as it hits the ground, its kinetic
Kinetic
energy.
energy is the highest, and
Yep,
potential is the lowest.
yep.
0.
So whenever we have a complete conversion of potential energy into kinetic energy, right? It would be like mgh is equal to 1/2 mv squared. That's the one for kinetic energy. And we can cross out m. And if we want to solve for velocity, we would just do like multiply the 2 on both sides, take the square root. So velocity is equal to radical 2gh. That is, so this is a shortcut formula that you can use for any situation where you simply have, like, I guess, a projectile being like dropped. Like,
Mhm.
so that would be like for a person dropping something like over, like, I don't know, a roof over here. It could be true for, like, if you had an inclined plane, what's the speed of the inclined plane at the bottom of the ramp? And then it can also be used for, you know, water coming out of a spigot, or in this case, like the hole of the side.
Mhm.
So
Okay.
now this is just asking about the height. So we just have to take this and we just want to rearrange it to solve for the height. So it'll just
So
be
yeah,
v.
so you square both sides, you get 2gh is equal to v squared
Mhm.
divided by v squared divided by v squared. Okay, so
Divided by 2g, you mean?
h is equal to 2gv squared.
So
Oh, I
well,
didn't do that
first,
right. Never mind. Hold on.
uh-huh.
First, you have to do the h. Sorry.
Yep.
2g divided by h. 2g over v squared. C. I got this time.
So wait, so from here you did
2gh is equal to v squared.
yep, 2gh equals to v squared. And
Then
then
I
yep.
divided both sides by h.
So if we want to find h, we want to isolate h,
I
right?
isolated it right, so I want it on the side where the v squared is. Oh,
Well,
I see what you're saying. I could literally just. Oh, I made that
uh-huh.
so much more complicated than I need to. It's just v squared divided by 2g.
Yep.
Oopsies.
No, you're good.
Okay.
But yeah, this could be a really good shortcut formula
Yeah. All right,
for
I'll remember
situations
that.
like that. Yep.
If I'm gonna be honest, when I was looking at this, like
Yep.
concepts, it made sense that it would be a principle or an equation, so I just guessed C.
Oh, okay.
I yeah. This
So yeah, uh so okay. Basically, so I'll talk about each of these. Like, so basically, gauge pressure is the pressure we saw earlier with that problem with
yeah.
PATM
Mm-hmm.
plus rho GH. And that can
Yes.
be used, I mean, that we used that in the example of like the manometer, but it but it's also used for, like, if you're submerged, um the pressure that you experience goes up with the depth. So that's
Okay.
gauge pressure.
Yes.
Archimedes principle is the buoyant force thing. It means, that any object that's submerged will, will have to displace its own weight. So we could say that, like, buoyant force is equal to negative, like, weight, which I will just write as Fg to not confuse it with work. Um, Bernoulli's equation is just applying conservation of energy uh, to volumes of water or fluid. So I'll write that some other time, but it's basically conservation of energy divided by volume. And so I'll just write it, whatever. So this plus that.
Okay.
And then the Reynolds number is something that involves. So, okay, so ideal, just like we have ideal gases, we have ideal fluids, and ideal fluids lack viscosity. So viscosity is something like honey. Like honey is like a
Like you
thick.
can't move through it.
Yeah, yeah, it's really thick. The flow within like the honey itself isn't really moving like, in clean kind of straight lines
Mm-hmm.
like water or something would be. So that thickness, that viscosity, if we consider that, that will cause something to behave as a real fluid rather than an ideal fluid. And so, oh, and then an ideal fluid will undergo laminar flow, which is in straight lines.
Okay.
And then the turbulent flow, think about those eddies, those whirlpools.
So that would be a real fluid.
Yep. And so this question's asking us, how do we know if it's laminar or turbulent, which could mean, in other words, like ideal fluid or real fluid, but also the main difference being viscosity, and Reynolds number is essentially like a measure of the viscosity.
Okay. I feel
Yeah,
like this is so
that
much that I have to memorize.
it's more so just an understanding, but uh you can have, I think I gave you this link
Did I
before.
isolate and just do physics, Anki, like stuff for a little bit? Or chem?
So I would say so you have like the Miles Down deck, I guess, right?
Yeah.
So there's an essential equations deck in there that's like 60 cards.
Yeah.
So I would
Cool.
get that.
That's you just put this in, right?
Oh yeah. I believe I shared this with you before. Um, but this like whenever you so as you're reviewing your CP content diagnostic, you can use this to learn about the topics. Like if you hit go back, oh yeah. So if you go back on that. So viscosity, well, like don't worry too much about this formula. Like don't worry too much about it, but you could see that, or me go forward. Wait, sorry. Like a few cards. There we go. That's our Ryan Reynolds number. So do you see here that this is what it looks like? Like I was not drawing it well, but laminar streamline flow looks like this. You see how it's going in lines?
Mm-hmm.
And then here we have turbulent flow where you see it's no longer going in
Like
straight
wind in a
lines.
building almost.
Uh-huh.
Like how the
Uh-huh.
building sometimes stops wind.
Yep. 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 So so yeah, this is, your regular airplane flight. And this is when you're experiencing turbulence. So you can see how instead of the wind and all that stuff going like cleanly like around you, it goes around you and then kind of swirls around and messes with the carriage of the plane. And you're gonna have to plug your laptop in
Yeah, I think it'll
be-
last.
because you're having a lot of those. You're almost reaching equilibrium in your battery, so
I
you need
remember
an
that.
electrolytic cell. But yeah. Oh yeah. So the Anki deck, essential equations, prioritize that. And there should also be a deck. Maybe there's a deck, or maybe we can find one for learning those functional groups, but that would
It just
also
cut
be
out.
something.
Like,
Hmm.
I don't know if it's me
Yeah.
or you that's like really cutting out.
I think so. Um,
Is it better now or worse?
it seems fine until I guess one of us gets cut off, but
Because you
um,
completely cut out like a little bit ago. I
yeah.
didn't hear
So
anything for a
yeah, so the essential equations Anki deck, and I don't know if there's one for this specifically, but I can find one for you. But like an Anki deck that would be for like the functional groups. Because thanks for sending me that screenshot. Because I was actually thinking like earlier today, like, oh wait, like I should check, if she's
this one.
learning that stuff. Yeah, yeah. And I sent you another one that has even more. Um,
It's
in an
probably the
email.
I have
Yeah. Oh yeah, that,
it's
that one's really good too.
I
But
have
yeah,
photos that you've sent me. I have a lot of stuff.
yeah. So it'll be like one of the most recent things that they sent. But essentially, like, it'll include things like aldehyde, ketone,
Hmm.
that kind of thing. That yeah. Oh, cool, you plugged it in.
Yeah.
So now you switch the signs and you're running that backwards.
Oh, sorry. I'm like
Mm-hmm.
learning how to do tabs, and if I
Mm-hmm.
close the MCAT tab, then it closes me out of what we're doing.
Oh
Okay.
yeah.
It might be like somewhere on my computer screen too.
Oh yeah.
If I don't
It's
know
okay.
about that. I have no idea right now. I'm sorry. I'll try to
Yeah,
find the other
don't
one.
worry about it.
Okay. All right. Okay, so I knew it wasn't these ones because it's just like a little too valence electrony, but the isolated negative point charge, so I assumed that like the middle would have to be negative. But then like I was thinking about like an electric field that wouldn't it go outwards instead of inwards? Like you wouldn't move electrons towards a negative charge, you would move them away.
So everything you said is true. Unfortunately, we've like people discovered electricity before discovering electrons. So by convention, electric field lines go from positive to negative.
Okay.
And current actually is in the opposite direction of electron flow. So
Okay.
uh so yeah,
Alright.
just remember those two things. Remember that electric field lines go from positive to negative
Okay.
always. And
Alright.
then current is opposite of
Opposite.
electron flow.
Alright.
Yeah.
So that's why it's this one, that it's just electrical going
Yep,
towards.
yep.
Okay.
Yeah.
Oh wow, I'm surprised I got this one right. And I can't remember what was bothering me when I was doing it.
Mhm.
I think it was literally just like the quadrupled, and then I thought that it would be like it wouldn't be as strong as a
So
force. Because like I was thinking like magnetically, like if you move things away, like the force between them decreases. And then since it's quadrupled, I thought it would be the inverse.
yeah, so it'll definitely be an inverse, so that you made the right assessment there. Now, if we doubled the charges, how do we know, what to do with the quadrupled? So like with this, we can see that the force has an inverse proportion with the square of the radius, and the force has a direct proportion with the charge. So if we make this charge 2q, right? They're saying the charges are both doubled, and we made this charge 2q, they would make 4q, right?
Yes.
And
But
then,
that's
uh,
okay.
And then if the distance, the radius between them is quadrupled, 4r, when we square this, we get 16r squared, right?
Mm-hmm.
So what we're doing to the force is we're multiplying it by 4, but also dividing it by 16.
Okay, so that gives us 1/4.
Yep. Does it make sense why it would be that?
Yeah, hold on, I just want to move the. I
Mm-hmm.
keep moving the zoom thing every time that you draw something so I can see the
Mm-hmm.
full.
Yep.
My thing is that isn't this for doubling it, not for quadrupling it?
Well, the distance is what we quadruple
Quadrupled, okay.
right here. But
4r
the
squared turns into 6. Okay, yes, I get it.
so
I remember you
some
saying like the doubling happened up here.
yeah, yeah. So let's say that um let's say that if the charges both doubled and but the distance between them is doubled rather than quadrupled, um what would be
It
the
would
electric
be
force?
8r squared. No, it would be, wait. Yeah, it would be 2r squared.
Okay.
And that would give us
Uh-huh.
4r squared.
Okay.
Yeah.
And then the
Then
magnitudes of the charges doubling.
that would still be 4. So it'd
Okay.
be 4/4, and you'd get 1.
Yep. So it wouldn't change, right?
Okay.
Good.
So if you're doubling everything, it doesn't change, but if the distances and okay, I understand.
Yeah, so it's just based on, these proportionality relationships.
Hmm.
Hmm.
Do we have time for more problems or
Yep.
this is a guess? I didn't know. I just like clicked one and I flagged it to go over.
Hmm. Yep. So the electric field is going to be so okay, just like gravitational field is like newtons over kilogram, meaning you experience a force of something in newtons
Hmm.
for every kilogram of mass.
Yeah.
For electric field, you know, uh, field strength would be the force you experience in newtons again, but instead of per mass, it'll be per coulomb because we're dealing with charges. So now you just have to deconstruct the units. So what
Okay.
could, yeah. So what could Newton be if you deconstructed that? Think back to F equals ma.
Mass times acceleration.
Yep.
I mean, is it force in terms of newtons? So wouldn't it just be ma substituted for like
Well, think about the units.
kilograms per? Since when is acceleration in terms of, wasn't it always meters per second squared?
What are
Like
you like comparing
for
that to?
that for acceleration, like I can't remember when we were looking at it and it was different. It was in terms of like,
That?
yeah, maybe.
Yeah. So like, you know, on Earth, the gravitational field strength is 10 newtons per kilogram. But if you look at F equals, wait, what?
I always learned it as like 9.81 meters per second squared.
Okay, but that's if we want to talk about acceleration, right? But if
Oh,
we want to talk about a gravitational field strength,
okay, I got it. So this is okay.
but it's still the same thing, right? Like
Yes.
look, F equals ma, right?
Yes.
And if you divide both sides by mass, F over m is equal to a. And if we're saying it's g, right? G, which is 10 meters per second squared, could also
Mhm.
be 10 newtons per kilogram.
Okay.
Because it's yeah,
Right.
because it's just rearranging this. So
And then the newtons can cancel. Wait, but I thought we need coulombs, not.
oh no, I was just explaining
Oh,
why
okay. All
why
right.
you see it this way also.
Okay.
But now, yeah, so yep, let's do the so mass is in kilograms and then acceleration would be in
Newtons per kilogram.
so
No.
we could use just the regular.
Meters per second squared,
Okay.
which is also ms to the -2, right?
Uh-huh. Yep. Now, so we know that this could be that, but now coulombs
Coulombs.
to amps. So an amp is equal to, which is a measure of current,
Mhm.
is equal to coulombs per
Per
second because
second.
it's the rate of charge.
Okay.
So for the so if we wanted
For
to solve
tricycle coulombs, you do amps per sec, amps times second.
excellent, yep, is equal to the coulomb. So here we could say amps times seconds.
Yeah, and since it's in the denominator, it's another negative s to the
Yeah,
-1, and amps to the -1, and that's how we get this third one.
yep. So then this becomes kilograms times meters over amps times, and then this S O squared would just be the one on the bottom. Like I could just put it on the bottom. So that'll be S cubed.
Okay.
Yeah. So being really flexible with the units and being able to, you know,
Move them around.
yep, shuffle them around and stuff is going to be very good for you,
Okay.
for everyone.
It's difficult. I think I understood this one, but I
Yeah.
wanted to make sure.
Hmm. What?
I was thinking of just like proportionality of it, like if one thing, like I found myself drawing out, like there was a problem at the very end that,
Hmm.
why does it say 0 seconds? Interesting.
Hmm.
Um, yeah. Uh,
Okay. Yeah.
I remember thinking of it as a proportion, and then I flagged it because I wanted to make sure that I like got it correct and that we could go over conceptually,
Sure.
but I'm glad I got it right.
So let's see. When a positively charged particle enters a magnetic field perpendicular to the direction of the field,
So
um,
it's like you have the field and then it goes in like this, right?
yeah, so let's say positively charged particle enters in, and let's say whatever the magnetic field, let's just say it's like going here or whatever. Um, the
Towards the
po-
negative side, right?
well, for magnetic field, like if it was an electric field, that would be from positive to negative. but
For magnetic.
uh-huh.
Isn't it like the positive would have to go towards the negative side?
So there's not going to be a negative or positive side for a magnetic field.
But don't magnets have like charged sides?
Nope.
What do you mean? Like,
North and south.
yeah, but don't
Uh-huh.
don't like the poles have a meaning? Like it beyond just north and south? Like isn't there like a magnetic
Uh-huh.
like two magnets from the same. Oh, it's
Yep.
just sides.
So like so yeah, it won't be based on the charge though. That's just the thing.
Okay. All right.
But electromagnetism, it is true that that magnetic force is a consequence of an electric force. You essentially get a magnetic field if you have a moving charge.
Mm-hmm.
And so, but the so like yeah, there sometimes will be an electric field involved, but in terms of magnetic field itself, it's not going to deal with like a charge in that way. But yeah, but there is, going to be like
Okay.
a north and south end and stuff.
Mm-hmm.
Um, but okay, so if it enters, so they're saying a positively charged particle enters into the magnetic field perpendicularly to the field, it moves in a circular path to the centripetal force. Now, this is where like the right hand rule comes in, where your thumb is going to be in the direction that it's traveling, the charge is traveling, and the rest of your fingers will be in the direction of the magnetic field.
Okay.
And then where your palm
Is the
is
circle.
um where your palm is facing out is going to be the direction of the magnetic force.
Okay.
So let's say here we have um you know a charged particle moving to the right, so I'm going to make my thumb to the right, and the magnetic field is moving up, so the force is pointing out of the screen.
Yes.
Okay, now that's kind of hard for us to do stuff with, so I'll do the same thing, but now I'll just draw it so that we have the magnetic field going like into the page. So, oh, sorry, this is out of the page. Oops. If it's into the page, it's like they're drawn as X's. So let's try that out. So,
The outwards one be like.
so the X's will go into the page. So we want these fingers to be going into the screen. And we still want our thumb to be moving to the right. So what direction is our palm? Yep, like that.
Okay. And then
So
things going out of the page, so it's.
so the your fingers are going into the page and your palm is just moving up, right?
Yeah.
So that means that I'll use green, that there's a magnetic field, sorry, a magnetic force going up,
Uh-huh.
right? And so I'm gonna use pink here. So since this is traveling to the right and the force, which causes an acceleration, is up, it'll go in this direction, right? Diagonally. Now, when it's here, its velocity will be going up. and the magnetic field is still going into the page, tell me what direction the magnetic force will be in.
Downwards.
So just do use the right hand rule.
Velocity is pink. Hold on.
Yeah.
You were doing the right hand rule.
Mm-hmm.
I'm using the wrong hand. That's why I'm like trying to make this isn't working. So then the force was going out of the page. So then
Well,
wouldn't it be like here?
sorry. So the force, so the down in the first example down there, the magnetic field is the thing that's going into the page,
Mm-hmm.
and your palm is facing up, right?
Yes.
So that's the force. Okay.
Right.
All right. Now do it for, so do it for this one here. So magnetic field is still going into the page, right? But this time our thumb is going to be facing upwards.
Yes.
Okay. So you can
Magnetic. Wouldn't the force still be going upwards? Or would it be going this way now, to the left?
yeah. So I think so you don't want to like bend your thumb. You want to keep it flat. So like a karate chop.
Okay,
So
yeah.
like so now that particle velocity is moving up, so our thumb is up. Magnetic field still going into the page, so it's still going to be, facing our screen.
But then the
Now the
force is going to the
force,
left.
exactly.
So then
So,
this would be in the middle.
yep. So now let's say it's up here, and this is the velocity, right?
Oh my God.
You could do it. Mm-hmm.
Like that.
Uh-huh.
And the force is going downwards.
Yep.
And your arrow is going to be in the middle of them.
Yep. And then it'll go here with the velocity going this way.
Force, arrow, diagonal.
Okay. Okay. So which way is the force?
Force is this way.
Yep. So
Diagonal.
this, yep.
Are we using quadrants now to figure out like which direction it's increasing, decreasing?
Well, we can now see that it produces a centripetal force
Uh-huh.
because it moves in the circle.
Right.
So see where it says that it moves in the circular path
Yeah.
given the centripetal force?
Yes.
That's why it moves in that path.
Okay.
So,
And then
mhm.
which ones would produce a decrease in the radius though?
Yeah. So now we can do, I guess. So first of all, this thing, I just want to make sure that makes sense, right? It'll move in a circle, essentially.
Yes.
All right. So that's the most important thing there. So now we know that this magnetic field, this magnetic force is going to be equal. We could set it equal to centripetal force. So magnetic force is going to be QVB, with Q being the charge, V being the velocity, capital B being the magnetic field. And centripetal force, which they're telling us is mv squared over r, they're going to be equal to each other, right? So we can set them equal to one another. So we get,
QV mv squared over r.
yep. And they're asking, okay, what changes to the magnetic field strength and the velocity of the particle. So if we can change the capital B and the V, what would cause a decrease in the radius here?
If we can change V and B.
Uh-huh.
Well,
Mhm.
how would you do this? Would you isolate R? Like, can you do like QVB over MV squared?
Okay.
You're left with QB over MV.
Yep.
And then if R goes up, but V stays the same, then R would be greater.
So we could see that B has a direct proportion to R.
Yes. And V has an inverse.
Exactly.
Oh, okay. So just B.
Yep.
Got it.
Good
Cool.
job. So, yep, we can end it
Yeah,
there. But
that's good.
overall, good job. Doing a great job.
So what
And
should I do like tomorrow and the rest of today before we meet? Because should I
yeah,
do a full length? Because we're meeting at 3, so I could technically finish. I just wouldn't have time to review it.
so I would say to review that content diagnostic that you just did, and you can review it and like read the solutions and see if the solutions make sense. If
And then
they
if not,
don't,
flag them.
yeah, if not, we can go over it when we meet.
Okay.
So do
You
that.
wouldn't do
And
full length tomorrow. You would just
no,
review.
we'll do it very soon though. Basically what I want before we do a full length is for us to completely cover that uh the content diagnostic that you just took,
Okay. All right.
and for you to also have all the equations down so you could use Anki for that. And then
Okay.
also, like, I'll try to find, there's probably like some Anki decks that are just with the functional groups,
Uh-huh.
but I'll resend that email.
Okay,
But
sounds good.
the
I can
functional
look through our
groups,
emails, like the ones that
yeah,
are.
yeah.
Okay.
So it'll be so basically what I want is for you to have seen like and reviewed the problems in that CP content diagnostic, for you to have all the formulas memorized, and for you to have all the functional groups memorized as well
Before I take a full length, not before tomorrow.
before you take a full length. Yeah.
Okay, just checked
And
it.
yeah, because now that means that once we go into the full length, we're going to know all the formulas, we're going to know all the functional groups, and we will have known all the different applications of all of that stuff. And that'll put you in the best position for that full length.
Sounds good.
Make sense?
Okay.
All right, awesome. You're doing a great job. Keep it up, and I'll see you tomorrow at 3
Yeah.
p.m.
All right.
All
Okay.
right,
Bye.
take care.